Hey kiddos, happy week 17. Today's goals are to assess your understanding of simple harmonic motion. You took a check for understanding quiz at the beginning of class. And today I'm going to introduce sound. I suspect today's lesson will be a little bit shorter so that you have a chance to ask questions, especially with regards to your IA. Okay. Before we start talking about sound, let's just take a little bit of time to refresh our memory about how waves work. Right, we talked about waves on a string, and we did that PhET simulation a while back. And then we looked at general kind of oscillatory motion with simple harmonic motion. And now it's time to look at another oscillation that is sound. And you can make sound in a lot of different ways, but it is still a wave. So let us talk in general about waves. On a string, if we remember, the wave speed was determined by the disturbance. The wave speed is determined by the medium. Right, the stuff that the wave is traveling through. Generally, the heavier or the more dense a substance, the faster the sound waves travels. So sound actually travels faster through substances like water, the ground, metals, than it does through air, okay, because the medium is more dense. And we'll look and see why that is true when we visualize a sound wave later on. Okay, so wave speed is determined by the medium. The frequency is determined by the disturbance. And the equation relating wave speed, wavelength, and frequency, right, remembering that this symbol here is the Greek letter lambda that represents wavelength. Okay. Now let's take also a moment to define the two types of waves. That says of. Let's try again. Okay, there are two types of waves. Transverse is what we expect it to be. Transverse is like a wave on a string, right? Where the direction of wave propagation is perpendicular to the direction of particle oscillation, right? The energy is traveling down the string, but an individual particle is just bobbing up and down. Okay. And then there is what's called a longitudinal wave. Or a pressure wave. Okay, and if you can visualize a slinky, you might have to visualize it because my drawings are not super good. Right. If we take a look at this, we've got regions of high pressure and then regions of low pressure. So this is called a longitudinal wave, known as a pressure wave or a pulse wave. And so what that is intending to show is that there is a pulse or a region of high pressure that is traveling through a wave. If we had a slinky, it would be like pulling back a bunch of coils of the slinky and then releasing them, and you'll see a pulse of high pressure, tightly coiled slinky coils moving up and down the slinky. So if we have a direction of wave propagation, I don't know why that's doing that. Let's unclick that, I think is the problem. All right, so the wave is propagating down the slinky or through the medium, but any individual particle on this type of wave, it's not bobbing up and down, it's actually moving left and right. Okay, so longitudinal wave, the direction of wave propagation is parallel to the direction of particle oscillation. Okay, that's a longitudinal wave. And again, a transverse wave up here, a transverse wave, the direction of wave propagation is perpendicular to the direction of particle oscillation. Okay. What's the world's simplest stringed instrument? It's really just a single string that you can pull tighter and tighter. I don't have one of these instruments at home, but I can draw you a picture. So what if we had an apparatus that was kind of like a table? And I could actually, a table with a little pulley on the end here. And what if I took a string and I attached it to the table? And then I threw it over the pulley and attached a hanging mass. Okay. I could pluck that string, pluck, 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 and it would play a note. It's not fancy. What would happen if I hung more mass on the string? Well, the tension would be higher and the note would be higher. Okay, so my question is, how could I quantify the tension on a single string? You could actually run a string over a ledge, over a pulley, and if you hang specific values of hanging mass on the end of that string, the weight pulling down on that string would be equal to the tension on the string, and that would be a way of experimentally quantifying tension. Okay. The string is going to stay the same length, so how could I change the frequency of the note? Well, you could add more mass, or you could simply pull down on that string. If any of you play stringed instruments, you know how we can change the note played on a string. I've got my little ukulele here. Okay. We know on a stringed instrument like this ukulele, right? Each of the strings is a slightly different length. Okay, slightly different length. And you can use these little knobs to change the tension on the string. Okay, so that's harder to quantify on our end, but we are changing the tension, and we can use specific tools like a tuning device to detect the frequency of the sound. Okay, you can also use your phone. Right, there's a tuning device on your phone that you can use to detect the frequency of the sound as well. Okay, so a couple ways that I can change the note that's being played on this string here. Okay, so I can pluck a string, right? And this is totally out of tune right now, I'm sure. Okay, pluck the string, and then if I put my finger down, a little bit down from the head of the ukulele, I get a higher note because I'm decreasing the length of the string. Right, so I could decrease the length of the string, Or if I start out there and I increase the tension, that's decreasing the tension. Right, I'm tightening this little knob up here. You can hear the string produce a higher pitch. So a couple of ways that we can change the note played by a string is to decrease the length of the string or increase the tension. Okay. Right, so on strings, there are different notes that can be played on strings, and the waves that are produced by the string tell us what sort of note is being played. Okay, so when you pluck a string on a musical instrument, you're producing a standing wave. Okay, you're producing a standing wave with two fixed ends, right? Both ends are tied down. Okay. And so when we're looking at standing waves, if you remember, we count the number of antinodes. So we count how many regions of bump there is, right? This counts as one antinode, this counts as another, and so this wave we call an n equals 2 standing wave. Right, this is an n equals 1, n equals 3, n equals 4. Okay, we count the number of antinode regions in the standing wave, how many bumps there are. Okay, and if we were to say the length of the string is from here to here, we could determine how much of a wavelength each standing wave is. So we could say the length of the string for an n equals 1 standing wave, how much of a wavelength is that? Right? If you think of a wavelength as one full up and down motion, a standing wave, a full wavelength would look like that. Okay, so n equals 2, the length is 1 wavelength. For n equals 1, the wavelength is half of a wavelength. We don't need that 1 there. N equals 3, the length of the string has 1.5 or 3/2 of a wavelength, and then this is, whoops, 2 full wavelengths. Okay? And again, this is with 2 fixed ends. There's a visualization that I wanted to show you. Just a moment. Okay, I don't believe you'll be able to hear the audio on this, but there's a musician who put his iPhone inside his guitar to record while he played. And you can see as he's playing the standing waves on the string. On the far left are the lower pitch notes, and on the far right are the higher pitch notes. And so you can see the higher pitch notes have shorter wavelengths like we expect, and the lower pitch notes have longer wavelengths like we expect. This is attached as a video on Canvas. It's actually a very, very beautiful music, and it's pretty relaxing. I recommend it.